No. Let's.
You're not.
There we go.
That way recording actually works.
Oh, so the recording works. Yep. Okay. Okay, so when you're looking at a circuit schematic, there's a couple of definitions you need to know. You need to know the number of elements. In this case, the circuit has 8 elements. You can kind of just number them, the sources and the resistors. You need to know the number of nodes. So I've highlighted the nodes in the light blue. So basically anything that connects multiple elements together is considered a node. A branch is basically an element. And then loops. So loops basically this is how loops work. You start from the source and then you go back to the source. But nobody really uses loops. Like I have no idea who uses loops, so don't even worry about loops. Just know it as a definition. And then you have meshes, which I don't know if she's covered this with you guys or not, but basically these little blue lines that I have here is considered a mesh. So everywhere where you have one entire loop that is just it's in its isolation. Okay, ignore loops. Like that's just a bad word because once you get to ENA, you're only going to be worried about nodes and meshes. So loops are useless. Yeah. So yeah, you'll learn a different method in ENA, and you'll understand why loops don't matter. But let's keep going. So Ohm's law is basically if you have a resistor and you want to take the voltage across a resistor, you need to take the voltage from one side of the resistor across it to the other side. So that's VA minus VB. So that's going to be delta V on top. I'm pretty sure y'all pretty much know all this. And then choosing the correct order of delta V is based on the direction of the current itself. So in this case right here, we have a current coming in to the positive terminal right here. Or the positive side of the resistor right here. So that means that V equals IR is just straight up like that. And if you have current coming into the negative side of the resistor, it's going to be V equals negative IR. And the same pretty much goes for power. These are your basic power equations right here. And then so if you have current coming into a component, you're going to have positive power. And what positive power means is it's going to be the element that is receiving that current is absorbing the power. So if you have current coming into a negative terminal of an element, you're going to have negative power. So a negative power means that that device is supplying power to the circuit. So resistors always absorb because they're passive components. So this is how you determine how you label your circuits. So, usually you draw out your schematic and you have resistors everywhere and you're like, I don't know how to label this. Just know that resistors always absorb power. They're passive components. And so that's how you know how to label the plus and minus sign on the thing. So, and this is just the equation for power. The sum of all power in a system. So the power absorbed plus the power supplied must equal 0. So let's move on to Kirchhoff's law. So Kirchhoff's law is basically pretty self-explanatory. Imagine you have a node right here, and you have multiple currents coming into that node and leaving that node. So it's basically the algebraic sum of all the currents coming into that node and out of the node. That has to equal 0. It's conservation of energy, basically. And the same applies to KVL. So KVL is the same thing as KCL, but with voltage. So the algebraic sum of all voltage drops around any closed path in a circuit equals 0. So basically, once you sum up all of these these voltages, they have to equal 0. And remember, whenever you're doing this method, you need to be like consciously thinking of you're doing VA. Like, so for instance, right here, you're doing VA minus VB. You're not, whenever you find a voltage, you're not looking like, oh, what's the voltage at like one spot, right? Because you need to know the voltage across something. Voltage requires 2 points. So I'll get into that here in a little bit. So basically, there's 2 ways you can basically label voltage and current. It's arbitrary, like how you want to label it. But most people, and I think I speak for most people, we do like a voltage drop from a positive side to a negative side. So the voltage across this element A is a voltage drop, because you have positive voltage on one side and negative voltage on the other side. You're losing voltage. That's a voltage drop. So then if you were to do the voltage opposite, so a voltage from, let me just do a little resistor here. If you wanted to do the voltage across this, but it was negative and positive, this is V1, this is V2, that would be a voltage rise, because you're taking the voltage from the negative side to the positive side, you're increasing the voltage. So just a quick, you can label it either way you want, but that's just the way I've done it. I think that's how Kogan does it too, right? Yeah, okay, cool. And then, so reference direction is just basically currents that enter a node are considered positive, currents leaving a node are considered negative, right? So let me just do this. We can do a quick, y'all want to do a quick like KCL, KVL problem? Okay, sweet. Yeah. So sorry, this is I didn't want to like just show you all the answer instantly, so I kind of wanted to work through it, Okay, so we have this circuit right here, and we want to find all voltages and all currents, right? So basically what I do when I start these problems is I try to identify every element in the circuit schematic. So let me take a drink of water real quick. So we have a 30 volt DC voltage source and 3 resistors. That's all we have in this problem. So basically, if we look for KCL at this node right here, we're going to have a I1 current coming in, because it's coming across this voltage right here into this positive resistor. That's how you know I1 is coming in. So I1, let me write this in quick. So I1 must equal the currents that are leaving, which is I2 plus I3. And then, so that's pretty much the only node that matters in this problem, because we're doing KCL for that. And then if we do KVL now, we want to do KVL for this mesh. I would get in the habit of calling these meshes instead of loops. So this is mesh A. So we're going to say that this is going to be KVL for this. So let me write this down, KCL. This is KVL. So KVL of A, I'm just calling this A. So let's start here. It's going to be V1, and it's going to be a voltage drop across this, right? And then plus V2 minus 30 volts equals 0. You're saying minus 30 because you're doing a voltage rise from negative to positive here. And then, so now we need to do KVL for mesh B. So mesh B would just be, it's going to be V3 minus V2 equals 0. And V3, because you're coming across this resistor, and then you're coming back up this way. And if you, oh, I lost connection. Okay, so real quick, you can obviously see that V3 is just equal to V2, right? So there's tons of different ways to solve these problems. Basically, the only method you guys probably know right now is like the very long method, which is like you have three unknowns, and then you have 6 equations. So 3 unknowns, 6 equations. That's not very good, because those don't add up, right? So basically, you have to do this by plugging and playing. So what we do in this problem is you take your friend Ohm's law, which is V equals IR for, so let's say, what is V1? So V1 is right here. So V1 would be, it's going to be I1 times 8, right? That's just V times V equals IR, right? So then V2 is going to be right here. So we're going to have I2 times 3, and then V3 is going to be I3 times 6. Is anyone lost right now? Because feel free to ask me anything. Just let me know. I'm going to keep going. So this is I3 times 6. So this is like the long way of doing it, very long way of doing it actually. Because if you could also think about this circuit as in, so we said that V3 was equal to V2, correct? Just by pure math. But if you also look at the circuit, you can tell that V3 and V2 are actually in parallel. So that justifies our answer. Like that has to be the case because they're in parallel. So basically what I would do at this point is start trying to plug stuff into these equations. And since we're kind of running behind a little bit, I'm going to kind of just skip ahead to the answers because there's like so much stuff we have to cover. So let me just grab this and I'll explain it. I'll explain it as I copy it over. I'll just stay on this one. Screw it. Okay, so I solved this earlier. Yeah, I solved this earlier. So let me just explain. So you have V1. Let me get my mouse. Okay, so you have V1, V2, and V3, and you could plug them into these equations, right? So what I would do is say this right here, V3 equals V2. So you plug in the V equals IR component of those. So this is V3, which is 6I3. This is V2, which is 3I2. So then you just divide by 3 of both sides. You get I2 is equal to 2I3. And then now this is a very good equation to have because now you have a new relatable equation that you can plug in. So then you have your KCL equation. I1 equals I2 plus I3, and then I2 equals 2I3 plus I3. And the reason why that is because you're just plugging in this V2 here. So then if you simplify that, you're going to get I1 equals 3I3 because 2I3 plus I3 is just 3I3, right? So now you have both of these. Now you have both of these equations in terms of I3. There's an I3 here. There's an I3 here. But you started off with I2 and I1, right? So that's the key there. And then, so now you have another KVL equation right here. This KVL equation. So V1 plus V2 equals 30. Now, if you just plug in what V1 and V2 is equivalent to, you have 8I1 plus 3I2 equals 30. Excuse me. And then, let's see, what did I do here? Okay, so now you plug in what I2 is here. And so you have 3, 2, I3, right? And then you plug in what I1 is right here. So you have 8 times 3I3. So now you have I3 is your only unknown in this exact equation right here. So basically, once you simplify all this math down, you're going to have I3 is equal to 1 amp. So that's very easy. So now that you have this equation over here, you can actually just plug directly in to these equations, which is what I did over here. So you have I1 equals 3I3, which is just 1. I don't know what's going on with the. Yeah. So you just plug those in. Now you have I1 and I2. So that's already, by solving for I3, you have all of the currents. You have I1, you have I2, and you have I3. So now that you have, you just plug in to this KVL equation. Actually, this is just the Ohm's law equation. So V1 is equal to 3 times 8. So this 3, I know I draw on a bunch of arrows, but this this I1 equals 3 amps. I'm plugging it in right here. So V equals 3 times 8. That's what this is right here. So that's just 24 volts. And then I'm taking this I2, which is 2 amps that we solved for, and plugged it in right here. So that's just saying V2 is equal to 2 times 3, which is 6 volts. And we know that V2 is equal to V3, so that's just 6 volts also, which there's tons of ways to solve this. This is like the very long method where you find all of these equations and you plug them into plug in and kind of brute force your way through it. Once you take E and A, you'll learn a lot more methods to solving this. But what you could have also done is just simplified this circuit down and say, hey, these two voltages are parallel. So you would just do your parallel equation for parallel resistors, and then you would just have one circuit, right? Or one mesh, sorry. And then that would be able to solve for I1. And then once you have I1, then you could go back and start plugging stuff in. It'd be a lot quicker. Whenever you guys start taking linear algebra, pay attention to Cramer's rule and row reduced echelon form. These are some of the most important methods of solving equations. So keep that in mind. Any questions on this problem before I move on? Cool. All right, so let's just discuss real quick what series and parallel passive components are. So what is a passive component? A passive component is resistors, capacitors, and inductors. They do not generate power or amplify any signals. That's basically what defines a passive component. It's passive because it absorbs power. It does not generate power, like it dissipates heat, you know. For series resistors, we have three resistors in series. The equivalent resistance is equal to the sum of all of those resistors that are in series. Pretty self-explanatory. Also, you should note, I didn't add this, but you should note that the current that goes through these series resistors will be the same throughout all of those resistors because you're on the same. So the current is not being distributed anywhere else. Now we have parallel resistors. Parallel resistors. So basically, parallel resistors are pretty easy. So this is what parallel resistors look like. And the way you define a parallel resistor is the top node has to touch the bottom node on both resistors, basically. Like that's the general idea of a parallel resistor. So I know the book and a lot of professors give you this equation right here, or it might be written differently for some of you. I don't know. But I would recommend using this notation right here. It's faster, it's more efficient, it's better, it's funner, more fun. Yeah, English is hard. So the equivalent resistance is basically 1 over R1 plus 1 over R2 plus 1 over R3, all to the inverse of that. This method leads to a lot of like accidentally typing something wrong on the calculator, right? It leads to a lot of errors, in my opinion. So I'm going to show you what this parallel symbol means and how to use it. So basically, this parallel symbol means that if you have, so say for instance, this is RA and this is RB, and I'm looking right here now. So parallel for RA and RB is product. It's called product over sum. So basically, you have RA and RB. So RA times RB over RA plus RB. That'll give you the parallel or the resistance value of these, and it'll condense them, right? And then what you would do is just do this same calculation for these two. So say this is RA and this is RB now. So what you would do is just do that exact same calculation, but they would be condensed now, and you would get the right answer. I'm going to show you how to use these here in a second. I just wanted to briefly describe that. Anyways, I need to fix these notes later. At the end of all of this, I'll try to upload this somewhere and you guys can look at it. So series inductors are literally the same exact thing as resistors. As far as series and parallel goes, they're not identical. They're both passive components. They behave the same. The difference between these two, there's a lot of differences, but I won't go into that right now. But let's just focus on the series and parallel parts. So resistors, inductors, identical as far as you're concerned right now. And then capacitors. So basically series capacitors and parallel capacitors are it's opposite. The roles are reversed. So to find the equivalent capacitance, you would do this formula that I don't use, or this one, which is better. And that's for series capacitors. So basically, it's just the roles are reversed. So parallel capacitors, you would see them like this, and you would just sum up all of the capacitors, right? Do a quick example. I've already worked this out. I don't want to go back and forth now because we're kind of running on time. So I'll just like leave up the answers and we'll just kind of work through it visually together, right? So let's start this example. So here's the circuit. Circuit looks like this from the start. So whenever you're looking at this circuit, it's asking you, what's the equivalent resistance, right? So basically what you want to do is find the source. This is the source, right? So you find the source and you want to work from the element that is furthest away from the source and condense backwards towards the source. That's how you want to work these. It's the fastest way to do it. So whenever you're looking at this, I'll explain this part in a second, but whenever you're looking at this circuit schematic, you can kind of see already that these two are in series, correct? So if you know that these are in series, you know that adding these two together, which is what I did right here in the equation, you have to add them because they're in series, right? So what I do is I just mark that out and say, hey, these are now in series. This is 360 ohms now. And I'll explain this notation. So basically the way this notation works is I do the series, and then so you would do parallel with 120, because once you simplify this, and I'll go down a little bit so you can see. Once you simplify this circuit, this is the simplified circuit, by the way, after you put these two in series. So notice here's the 360 that I talked about from here. So this 360 is now in parallel with the 120, right? So since that 360 is in parallel with the 120, you would just do the parallel equation, which is the one I use, which is right here, this one. So it's just a product over sum. So if you really wanted to write it out, I'll just say this is a 120 times 360 over 120 plus 360. That's the equivalent of this. And if you calculate that, that's 90. So that's where this 90 is from. So let me erase this. Okay, so now once you simplify this circuit, you're going to see that these two right here are in series now. So you've simplified this part, and you know that those two were in parallel, but now they're in series. So now these two are in series, right? I hope I'm explaining this properly, or explaining this clearly enough for you guys. But so and then these two are in series now. So when they're in series, you add them up. This is 180 ohms now. And then so basically I'm just kind of describing what I'm doing here in this equation. You're doing the product over sum plus 90. And so once you calculate that, it's going to be in parallel. I'm going to show you the last part of what the circuit looks like. It's going to be 180 in parallel with 360 now. That's the final step. So then once you do the product over sum again, you're just going to condense those down, and then you're going to be left with just this circuit. So basically, if you calculate all that, the equivalent resistance is 120 ohms, and the voltage, now that you have this circuit simplified, you have V source, which is Vs right here, and then you have I source, which is just this I right here, Is. So this is Vs and Is, and then it's just Ohm's law, but in an equivalent resistance mode. Basically, it's the same. You can apply Ohm's law to equivalent resistances as well. Excuse me. So basically, this is a current source, by the way, that is 30 milliamps. So this 30 times 10 to the negative 3, that's what that's representing, times 120 is equal to 3.6 volts. So now you know the total voltage of this system is 3.6 volts. And yeah, so let me go back and I'll just recap this real quick. So let me explain this notation real quick. So ignore all that, and we're just going to stick right here so I can explain this notation. So what I do is I start from the farthest right, and I say those are in series, so I'm going to put those first. So I'm just going to rewrite it up here. So Req is equal to 160 plus 200. This is gonna require a lot of brackets to do this, but it's worth it. So now I can scratch. So now I can mark this off, right? I know that those, and you kind of visualize this in your mind. So now I know those. So now I know that this is a 360 right here. So now I know that 120 is in parallel with that, and I would do parallel with 120, and then I would bracket those off together. And then now that these are all taken care of, you kind of visualize this in a little bit. Now that those are all taken care of, you can kind of imagine that this resistor is now in series with all of these that you computed, right? So now I would do plus 90 and then bracket that off. And then, so now you know that this 90 and then this one that was these all together are in series together. And then finally, those two would be in parallel with this 360. So you would just say parallel 360. And the way you calculate that is start from the inside parentheses, sum that up, and then calculate this. So it'd be 360 parallel 120, running out of room. And then you would calculate that, and then you would do that value plus 90, that value parallel 360. I want to show you all just a real quick. I know that's maybe confusing a little bit, but I just want to show you a real quick example of why this is so powerful. So this is a very complicated looking circuit, right? You can actually solve this entire circuit with one line, and that's what I've done here. So if you know how to read this and you know how to apply this complicated circuit, you can just literally say, and I'll show you how to do this, or I'll post this later so y'all can practice. But you could just solve this entire circuit with one line. So that's kind of why I wanted to show you that. What's up?
She's never used that parallel symbol in class, so who would use that on her test, like for example,
Yeah.
partial credit, like would she, I don't know if she,
I think she would give you full credit. Here's what I would do. I would draw the parallel symbol and say, hey, this is equal to RA, RB over RA plus RB. And this is just saying that this equation, the product over sum equation, is equal to that parallel sign. So anytime you use that parallel sign, she'll know exactly which equation you're using. So you can do it, but just make sure you notate this, because or else she's going to be like, what is this? You know, she needs to know what that equation is, which most people do. Like most people use product over sum equation because it's faster, easier to calculate. You can
write down all the numbers and parentheses on the paper.
Yeah, so the way this one would work, let me just try to real quick run through this. So we're starting from right here because it's the innermost parentheses. So this one right here. So 6 is in series with 14, right? And then once you get that amount is going to be in parallel. I don't know what it is. That amount is going to be in parallel with 15 right here. So you calculate this, and then you get rid of that. So now you know that you have a resistor here that is in parallel with this 20. So now you say, hey, this whole value right here is now in parallel with 20, which is right here. So you calculate that, and then you can get rid of that. So now this whole value is in parallel with this 4. So you calculate all of that, and you get rid of that. So now all of that amount is in parallel with this 12. And then you can get rid of that. You can say all of that amount is now in series with this 16. And so you get rid of that, and you say now all of that amount is in parallel with this 18. So you're going there, you get rid of the 18. So now this whole entire resistance, all of this resistance is now in series. If you imagine all of this is gone over here, that whole amount is right here, but it's in series with 8 and 10. So you just take that whole amount and say plus 8 plus 10. And that's it. It's very useful. I know it's kind of daunting at first, but I recommend you all practice it, because once you get to ENA, this is very, very quick handiwork, and it's actually an acceptable method. And actually, it's even taught in ENA, I'm pretty sure. Anyways, so we're gonna move on. Yeah, we got some time. So, sorry. Let me go back. Was there a question? What's up? This one? Or this one? Okay, so yeah. Okay, so let me redraw this. I'm gonna redraw this part over here. So that's what you're talking about, right? So let me say I need some room. Okay, so I'm gonna say that this is the 20. I know I'm kind of drawing sloppy, but we have a lot to talk about. So let's go through here. Okay, so you're talking about this, right? Okay, so whenever you put these two, because you're starting from the furthest to the right. So whenever you put these two in series, this is what happens. And this is your new resistance, right? Okay, so now you know all three of these are in parallel, essentially. But you could think of it like this. This is what your new circuit would look like. So now you know that this amount that you added together that was in series is in parallel, parallel, parallel. That's these. You kind of see what I'm saying? Okay, cool. I'm hoping I'm explaining this good enough for you guys.
Based on like the nodes, like you know how she teaches you to highlight each and every like node and branch. So like whenever it's the same node, they're connected, then you always know they're parallel. So you can also use that to help a little bit visual it.
Okay, let's quickly go over voltage division. So the way voltage division works is, let me get rid of this. So a voltage divider circuit is a circuit that produces two or more smaller voltages from a single voltage supply. So you have this voltage supply, and a voltage divider is basically two resistors in series. That's literally all it is. Don't let anybody confuse you. That's really all it is, because the reason why is because if you say this is 10 volts, or no, let's say this is 20 volts, right? That means that the positive side of this resistor is also 20 volts. But in here, you're going to have something that's less than 20 volts. We don't know how much yet, but you're going to have something that's less than 20 volts because, again, you're doing a voltage drop across that resistor. And then you're going to have, this is ground. So this one will be 0 volts. Okay, so this is a voltage divider circuit. It's as plain as it looks, basically. This is the equation you would use to find the voltage drop across V1. This is not saying, hey, what's the voltage at V1? Because that's kind of incorrect terminology. You don't want to find V1 if you're trying to explain to somebody, you don't want to say like, what's the voltage of V1? You want to say, what's the voltage across V1? Because again, voltage takes two nodes to take the measurement of voltage. So these are the equations you use. And yeah, so for voltage dividers, one thing you need to know is the current is one current. It's not split up into anything. So the current remains constant throughout this entire circuit. And this is just like, if you wanted to do voltage division for an infinite number of, you could say this is like, you could say this is like 300 volts, and you wanted to divide up your voltages amongst all of these resistors. So this would be like 215. I'm just making up numbers. This is 125, blah, blah, blah. Like basically that's how you chop up your voltage, right? Okay, so let's do the current divider circuit real quick. Has she talked to you guys about current division? Okay, so let me just quickly explain it real quick. So a current divider circuit is just the polar. It's like the opposite of a voltage divider circuit. It's pretty much the same thing. It's simple, not the same thing. It's as simple as the voltage divider circuit, I should say. So current divider circuit is a circuit that produces two or more smaller currents from a single current source. So if you have a current source here, this is what a current source looks like. It has the arrow in it. So you have a current source producing current. That means you're going to have one voltage across this entire thing, the voltage on top, and then you're going to have ground down here. You're going to have ground. So that's going to be 0 volts, and this is going to be whatever the voltage is. So these are the equations you would use to solve a current division problem, only if you have 2 resistors in the circuit. So same thing with voltage division, I forgot to mention. These equations right here, and nobody ever tells you this, like nobody told me when I was learning this. So these equations are very, very, very useful, but they're only used if you have 2 resistors. So if you have 3 or more resistors, you have to use this general formula, which is this Vj equals Rj over R equivalent times V source. So again, this is if you have 2 or more, like not 2 or more, if you have at least 3, you need to use this equation. But if you only have 2, you can use these 2 equations. And I know that's like no one ever told me that when I was learning this, so I'm letting y'all know now. And then the current divider circuit, these 2 equations are identical. They are not identical, but they're similar in the fact that, oh, go ahead.
There's this restatements of Ohm's law.
Yep.
You can just use like KVL, KCL, and Ohm's law. You don't technically have to do it.
Yeah, you can actually. There's videos on YouTube where it shows the derivation of these current dividers and voltage dividers. They're out there. Yeah, but it is just Ohm's law essentially. Yeah, good question. And so the current divider circuit. Oh, sorry.
You know on the previous one how you had 3, right? You had 3 of them.
This one, right here.
Yes, you know how like you said if you have 2, you can use that one. But if you have more than if you have 3 or more,
yeah,
then you have to use that one.
Right.
Would you be able to do what you did on the other one where you started combining them to get to that 2?
Yes, you definitely could do that because if you think about it, all of these would just be an infinite amount of series resistors, right? So you could say all of these resistances. So what I would do in that case is I would do this. If it was just like say 5 resistors, like this one here. Sorry. So say for instance this was the circuit, and I know this is kind of abstract, but this is the circuit. There's 5 resistors, right? So what I would do is I would combine 4 of them, and then you would say, hey, this is like 4K. Like say they're all one. Say this is like 1K, 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 1K. So say this is 1K. This is like 2K. So this is 2K ohms, by the way. So I would combine all 4 of these and say, hey, this is 4K, and then I would just apply that formula.
Okay.
Yeah.
Just leave the resistor you want by the voltage across. You leave that one, and you combine the rest.
Yes, because the reason why is because, and let's just do an example real quick, and I'll show you what I'm talking about. But yeah, you're right. So real quick, let me just summarize current division, and then we'll move on. So current division is just you have a current that's produced by a current source, and you're going to have a single voltage across these 2 because they're all going to be in parallel. And the way that current works is as soon as current is coming this way and it hits this node, it has a decision to make. So this is I. It's the full amount of the current. It's the full amount of the current source. Once it hits this node, it has a decision to make. Well, it can either go this way, 10K ohms, or I could go this way, 2K ohms. Well, the answer is it's gonna go both ways, but it's gonna go more towards this way because 2K is less than 10K. So current likes to pursue the path of least resistivity. But basically, once current hits this node, it's going to split off into both directions. Now you're going to have I1, you're going to have I2, you're going to have 2 different currents. So this is basically if you have a big current and you want to divide up this current amongst many parallel nodes, parallel branches, then that's how you do it. And yeah, what you just mentioned is what I have right here, actually. So if you wanted to do that notation with with it, you would do it just like this. So let's work this. This is just a quick example I just wanted to show you guys to get some actual application out of this. So this is 10 volts, and we have V1, the voltage across V1 and the voltage across V2. So if we use this formula right here I'm looking at, so this is going to be the voltage across V1 is going to be the voltage source times the resistor, this resistor, R1 plus R2. So that's the formula we use. And you just basically plug in these values. You're going to get 10 with 4.5K ohms over 4.5K plus 2K. That's going to be equal to 6.2 volts. Now, there's two different ways you could do this. You could say, what's the voltage across V2 now, right? You could do this whole thing over again, or you could just realize that you had 10 volts here, and then you dropped 6.72 volts. If you just subtract those two numbers, that's what V2 is equivalent to, because that's the only voltage that's left. So instead of doing all this math again, you could just simply say 10 minus that voltage drop. Well, now I know 3.28 is that voltage at that spot. So any questions real quick before I move on? All right, cool. So let's get to sinusoids, very fun stuff. So sinusoids, basically, if we have a voltage V of t right here, basically if you have a voltage V of t, basically what that's saying is the name of the function is V, voltage, and you're in the time domain t. And so basically that is equivalent to Vm, which is the amplitude of the voltage, sine omega t, where omega is the angular frequency. So these conversions right here, these conversions right here are just a way to get from radians per second to hertz or seconds to hertz. That's really all that is. So you probably know, has she went over this with you guys at all? A little bit, or okay, cool. So so you guys aren't completely lost here. So so a sine to cosine conversion is basically if you get a function, and we'll do an example here in a second, but if you get a function that is in terms of sine, you have to convert it to cosine every single time. And there's a complicated explanation for that, and I'll try to explain it here in a second, but just take that for what it is for now. You have to compute things in cosine, and the reason why is because cosine is the real part of the phasor. I'll explain what I'm talking about in a second. Sorry, I am. I had an interview earlier with TI, so I was talking a lot. But anyway, so yeah, so this is how you add two sinusoids. Sinusoids does not mean a sine wave. Sinusoids means cosine or sine. I know sometimes that's confusing. And I drew this pretty little diagram for you guys. Basically, you have a sine wave here, and I'm just identifying each of the parts for you so you can understand all of the elements of the sine wave. So T is your period. A period is one cycle. So one cycle is the time it takes to get from where you started back to where you started, like over time, you know what I mean? That's one cycle. I know this is like kind of rough drawing, but yeah, so that's your period, which is one cycle. So V peak or VP is just from the time axis to the top amount of the amplitude right here. So that's 5 volts in this case. And V peak to peak, or VPP, is going to be the peak to peak voltage from the max amplitude to the minimum amplitude. And so the minimum amplitude is right here, which is -3 volts in this case. And then that's just VP min, VP max. So basically it's just like identifying the parts for you. So the V peak to peak in this case would be 8 volts because you're going from 5 volts up here to 3 volts down here. That's what V peak to peak means. You're encapsulating the entire voltage. Do I have enough time? Okay, so I'm going to try to explain this real quick. Basically, complex numbers are hard. So they're very hard to explain as well, turns out. So let me try to explain what I have drawn right here. So basically, if you can imagine this circle right here, and you'll learn this if you ever take advanced engineering math, you'll learn this a little bit more about this. So imagine you have this circle right here, kind of like the unit circle. And this axis right here is called your real axis. So by real, I mean what is tangible, what we can actually use in math. We can use imaginary numbers in math, but they're not, they suck. So, so this is the real part and this is the imaginary part. So this is the imaginary axis, this is the real axis. So I'm just letting y'all know that right now. So imagine, I tried to draw an eyeball right here. So imagine you're looking at this circle on a flat plane from this side. So you can't see anything but the height of, so say you're looking right here at this dot right here. So where I says start. So imagine you're looking at that. So if you can imagine this circle right here is going around this at a constant rate, just like that, just going around this at a constant rate. And you're looking at it from the right side, right? So if you're looking at it from the right side, all you're going to see is this, right? You kind of get what I'm saying by saying that? You're only going to see this dot going up and down like that. So that is a sine wave. If you imagine it, that's what a sine wave is. So now, if you were to look at the bottom, I tried to draw an eyeball right here. If you were to look at the bottom of this and do it the same thing, you're going to only see this right here, back and forth, back and forth. If you were to imagine you started from right here and this was just going around like that, right? So if you were to look from the bottom, you would realize that if you started here, that's where a cosine starts, right? So that is literally a cosine wave. So since your real axis, which is your x component, is where you would be observing this from the bottom, this whole zone right here is your real part, which is your cosine part. And then this whole part over here is your imaginary axis or your sine component, your sine wave. I hope this makes sense because this is my first time trying to explain this to somebody. So yeah, you have basically your y component, which is jy, which is considered jy in rectangular form. So you have a r equals x plus jy, right? So this part is your imaginary part. This part is your real part. So that's kind of how that is interpreted. So and the coordinates around this circle are right here. R is your x component and theta is your y component for phasor notation. So let me come down here a little bit. So if you imagine, let's just not describe this. Let's just ignore this part for now. It is important, but we don't have enough time. So imagine e to the j omega t, because omega t is your, okay, so theta is equal to omega t. So imagine this is just e to the j theta. It's the same thing as e to the j omega t. They're equivalent. So your cosine omega t is your real part of the function, and j sine omega t is your imaginary part of the function. And basically, how you can visualize that is cosine, the one we all know and love, that is on theta. So this is theta. So just a regular cosine goes to 2 pi, right? So it's how to interpret that in the frequency domain, or sorry, the time domain, is you just change the theta to time. And now one cycle of a cosine wave is the same thing, but instead of 2 pi, you're going to go off of your period, which is t, which is 1 over the frequency. So that was a lot to explain. So I just want to real quick, do you guys did that help at all? I don't know. Yes? Okay, sweet. So let's move down here. So real quick, we don't have that much time left, but so let's talk about phasors. A phasor is a complex number that represents the amplitude and phase of a sinusoidal signal. So its rectangular form is represented this way right here. And you know that x is the r cosine theta component, y is your r sine theta component. So that's what the imaginary function z looks like. And z is basically impedance, if just for letting you guys know. So the polar form equivalent of these is going to be z equals r theta, which I don't know if y'all, I should explain this too. So z equals r theta is also equivalent to r e to the j theta. And the reason I mention this is because you're going to see this form in advanced engineering math, and you will never, well, okay, I won't say never. You will hardly ever see phasor notation, at least on campus that I know about. But you will run into math classes where they look like this: r e to the j theta, r e to the j omega t, and you're like, what's happening? At least I was. So whenever you write something that's z equals r theta, it's implied that e to the j is inside of that phasor. It's hidden. It's implied that it's there. Nobody tells you this, but now you know. So r is equivalent to the magnitude, which is square root of x squared plus y squared, and then theta is equal to the inverse tangent of y over x. So z, which is impedance, which is complex, this is in phasor form, so that's just the equation for that. So I think we're out of time. I could keep, I don't know which one.
I mean, we have the room for this next hour, and genuinely, I forgot how much stuff is covered in 1202.
Dude, it's so
You
much.
might want to keep going with this stuff if you guys want to stick around.
Okay,
Are
so
there any other, like, because we can get to 2310 stuff after, but like, this is important stuff and it's kind of complicated.
yeah, okay.
Literally complicated.
Let's just do a quick. Okay, let's just. I'm almost done with this part actually, so we'll just keep going. So the typical operations, at least how Kogan describes them, that I know about, is you have addition and subtraction, which is rectangular form. So if you have z1 plus or minus z2, it's going to be equal to the x component of the first z plus or minus the x component of the second z plus j right here. And then the y component of the first z plus or minus the y component of the second z. So basically that's just saying you can simply just add or subtract them together. And I think, have y'all done these yet? Like, okay, sweet. All right, so if you were to multiply or divide, you can't do it in rectangular form. You have to convert it to polar form. That's just probably the simplest way to do it. So let's just do a quick little demonstration. So this example, say you're given this function right here. And that's the function. They're like, convert it to phasor form, right? So we know that v of t is equal to Vm sine omega t. So Vm is right here, and then I should say plus phi here. So this value plus phi is right here. So basically, you just literally translate this notation into this notation. It's just verbatim, So that's how you do that. And so whenever you have a phasor, you need to kind of understand that you're messing with an imaginary number. It's a complex number. So what I wanted to get to you guys, or what I wanted to say to you guys, is e to the j theta is implied in this notation. Whenever you see a phasor, there is an e to the j right here in between there.
I think we're dealing with the exponential form at all.
Yeah. Oh, I know you're not, but I wanted to introduce you guys to it because you will be running into it like tons, like in the future. So just, we're not going to do any calculations with the e right now. I just wanted to show y'all that it's there, and it will show up again. Like, you can guarantee that. So this is actually what the phasor looks like, but it's just shorthand notation. So say you have this function I of t, 10 sine 1000 t plus 20. Okay, so a sine function is just a shifted version of cosine. So what I mean by that is, if you have this x and y axis, if you have a sine function like this, so this is just a shifted version of a cosine. So a cosine looks like this, right? Because sine starts at the origin, cosine starts at 1. So this shifting amount, so say you have sine, I'm just going to move sine around. So say sine is shifted way back here. I know this is a terrible drawing, but say sine is shifted to the left behind your cosine. So this little gap, sorry. Yeah, this little gap right here is that's your phase shift. So that's why we kind of have to do everything in terms of cosine, because cosine is the real part. And yeah, so let me move past that. So in order to translate this function to something useful, which is cosine, you have to take the function right here and just subtract 90 from it. And so you'd get negative 70. And that's just part of the definition that we saw up here, right here. So if you have a sine function and you want to convert it to cosine, you literally just subtract 90. So let's go back to this. So if you have an example that wants, so say you have a z function, z equals 3 plus j4, and then z2 is in polar form. So this is in rectangular, and then this one is in polar. So they're incompatible types, right? So in order to work with these, what you would need to do is convert this z1 into its polar form. So in order to do that, you just use this equation right here. So you literally just plug everything in. So what you would do is z1 is equal to the square root of x. Here, I'll just go along with it. So this is equal to the square root of x squared plus y squared, and then inverse tangent, sorry, of y over x. That's what this is right here. And so once you plug in all those values, you'll notice that this is the answer. So this and this is just the rectangular form, and this is just the polar form. So they're equivalent, but they're in different states. And here, yeah, they're just basically two different ways to work with these values. So Z2, if you have Z2, it's in polar form. You need to convert it to its rectangular form. So you have 13 to the negative 22.6. So in order to convert that back, let's go back to our formula. You're going to basically have to do this one right here to convert it back, right? So to convert it back, you would just say 13 cosine negative 22.6 degrees plus j, and make sure you include the j. So plus j, 13 sine negative 22.6. And this is the answer. And the reason you get this answer is by literally just typing in your calculator 13 cosine and then parentheses negative 22.6, hit enter, is 12, right? And that's how you get this value. You just literally type it in your calculator, 13 sine negative 22.6. And you're going to see that it's like very, 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 very close to 4.99 or 12.0001, whatever. You can round for these because you don't want to do like rectangular form addition or subtraction with decimals. So yeah, so then in this case, now you have your Z1 in rectangular and polar, and you have your Z2 in rectangular and polar, right? You have both of them in the forms that you need to work with. So let me see if I have something here. So basically, there's all kinds of things you could do here. I didn't make up a problem, but you could do Z1. Oops. Now that you have both of them in both of their forms, you could do the Z equals Z1 plus Z2, or you could do Z1 minus Z2. So this would just be what? So we would take 3 plus J4, and then we would add that. So plus 12 minus J5. And you can just literally add those together. So this is just going to be 3 plus 12 would be 15. And then we would have minus J. And then if you subtracted them, you'd have the same thing, but you would just subtract them. I wanted to show one more thing before I hop off here. So impedance represents the opposition that the circuit exhibits to the flow of a sinusoidal current. And you can basically generalize Ohm's law with that by saying this is just voltage, V, and then this is Z times I, basically, but it's in phasor notation. Oh, what's up? So if the X value is negative, like right here, I'm sorry, repeat it again. Uh-huh.
If you typed in a negative number to the tangent function, that
Mhm.
should return the correct value. But yeah, I would say make sure that you're in the right quadrant.
Yeah, definitely do that.
Where if your rectangular form X is negative,
Mhm.
then you make that positive, you add one.
Yeah, that's right.
That's not.
Okay, so let's just wrap this up real quick. So these are the primary equations you'll use for RLC circuits in this class. So this is just saying that the impedance of the resistor is just equivalent to R. And the reason why is because R is just R is a real component, and it doesn't have any reactive pieces to it. And what I mean by reactive is it only dissipates real power, basically. So your inductor, Z of L, is your impedance to the inductor, which is this equation, J omega L. And then your impedance for the capacitor is ZC is equal to 1 over J omega C. And I recommend that you guys also use this equation too, because 1 over J is just equal to negative J. And sometimes this will save you. It's like a lot easier to work with for a lot of problems. So make sure that you know that these are equivalent whenever you're solving those problems. Have you guys done any complex impedance problems yet? Okay. Have y'all done like a RLC circuit in series or parallel or both? Both? Okay. So I'm not gonna have enough time to do one of those right now, I don't think, but I just wanted to wrap up with this. So yeah, so this is your real axis and this is your imaginary axis. And did she tell you all about like Eli the Iceman or whatever?
Yeah.
Okay, so Eli the Iceman is basically just indicating. So Eli the Iceman is basically just indicating if you had a sine wave and you had another like cosine. This is just saying like say this sine, or sorry, say this signal is current and say this signal is like voltage. This is basically just saying like I is your current signal and V is your voltage signal. So I would be lagging voltage in this case, right? But let me just explain this part real quick. So basically, if you have a Z that is greater than 0, you're going to have a more inductive circuit. And if you have Z that's less than 0, you're going to have a more capacitive circuit. And that's just based on like, I think that's just based like you're going to have more of one type of energy storage in your circuit. So like either a more magnetic energy storage or a more electric energy storage. Okay, so here's a really quick shortcut. This is the last thing. So have y'all went over like just basic complex numbers? Like have y'all talked about this where J, y'all know J is equal to square root of -1? Okay, so yeah, J squared is equal to -1 because if you had negative square root of 1 times negative square root of 1, you would just get -1. Yeah, and then so J cubed would just be negative J because you'd have negative square root of -1, and then this is just J. And then j to the fourth power would just be j squared times j squared, which is just -1 times -1, which is just +1. And then finally, you'd have j to the fifth, which is just 1, which is just j to the fourth times j, which is just 1 times j, right? So those are complex numbers. And then, so one thing you should know is the number of solutions for the z is equal to the order of the polynomial. You'll need to know that for advanced engineering math. And then here's a quick example of how you could like shortcut some division. So if you have z is equal to 2 plus j over 3 minus j, that's remember you'd have to convert that to polar form to divide these. Well, a quick shortcut you could do is just multiply by the conjugate. And what that does is it makes your denominator real. So it makes it a real number, basically. It makes your denominator not complex. And that works for any time you have a complex number and then denominator. If you want to just multiply it by the conjugate, you can actually turn it into a real value. So the way that works is if we have this, and then we want to multiply by the conjugate, so it's going to be 2 plus j times 3 plus j over 3 minus j. And y'all know that the conjugate is just the inverse of this one right here, right? So that's what I mean by multiply by the conjugate. And so and then when you multiply these together, you're going to get so 2j, 3j. So it's going to be 6 2j, 3j, j squared. So it's going to be 6 plus 5j plus j squared. And then the bottom one would just be 3 negative j, 3j, be 9, 3j, negative 3j, negative j squared. So these would cancel. So it'd be 9 minus j squared. So that's what your denominator would be. But if you notice, there is a j in the denominator, but j squared is just -1, right? So you could just say, hey, this is -1. So 9 minus -1 would be 10. So that's how you turn it into a real value without having to convert it into a polar form. So this would be your final answer without having to convert to polar form. That's all I got, and like a little bit over. So hopefully that was helpful.
To answer your question earlier about being worried about being in the wrong quadrant,